Welcome to the UGC lecture series. In this lecture, we are going to continue about database management, in which we are going to look at basically we are going to look at record organization. In record organization, we are going to talk about how the records are stored and how it is buffered and what are the issues in recovery also, because that is very important as far as database management is concerned. So, the objectives of this lecture are to summarize recovery algorithms, which we have already seen before, to introduce the different type of storage structures, to understand buffer management policies and to discuss the various file organizations. So, these are issues that we are going to discuss. So, let us first look at issues of data access and to discuss the recovery and issues of atomic properties which we are going to ensure. So, first of all, let us we have already looked at recovery algorithms, but just let us tell what are recovery algorithms. Recovery algorithms are techniques to ensure the database consistency and in transaction atomicity and durability are present in spite of failures. That is what is recovery algorithms. And when we talk about recovery algorithms, they have basically two parts. The first part we can talk about is the actions that are taken during normal transaction processing. So, some bookkeeping that we do to ensure enough information exists to recover from failures. So, if we did not want to recover from failures, then at that point of time recovery you do not have to do so much of management or bookkeeping as we call it. So, during normal processing itself we have to do lot of bookkeeping. And the second part of recovery algorithm is the action taken after a failure has occurred. And so that you bring the database contents to a state that ensures the three properties of atomicity, consistency and durability. So, bring it to that state. For that you have to do that after the failures occurred. So, basically we are talking about two parts, one during normal operation where you do the bookkeeping and one during failure to take action when failure occurs. Okay. So, that is about the recovery algorithms. Now, let us talk about storage structures. So, this lecture is basically going to be about storage structures. When we talk about storage structures, there are different types of storage structures. So, the first one that we are going to talk about is volatile storage. Volatile storage is one that does not survive any system crashes. Example of such storage systems are main memory and cache memory. And then we talk about non-volatile storage. These are storage systems that survive system crashes. Examples are disk, tape, flash memory and non-volatile RAM that is which is has a battery backup. Then you talk about what is called as stable storage. Stable storage is actually a mythical form of storage that survives all failures. So, this is not actually possible, it is only an idealistic view, but this can be approximated by maintaining multiple copies of data in distinct non-volatile data. So, you do not have a system where in spite of any system failures you can ensure that it survives it, but what you can do is you can have multiple copies to sort of simulate that ideal situation. So, now let us look at stable storage implementation. In stable storage implementation, as we already told, we are going to maintain multiple copies of each block on separate disks. I will talk about block a little later, but here you assume it is just a portion of the database. So, we are going to maintain each block in separate disks, and you can also have copies at remote sites, so that you the multiple copies, some of them can be at remote sites, so that you are ensuring protection against disasters such as fire or flooding, because if you stored it in the same building all the multiple copies can be affected. So, stable storage implementation, even there you can have failure. When can you have failure? When during the data transfer there is some failure, then that time you may land up, that is you have copied one copy and the process of copying the other one there is a failure, then you can have inconsistent copies. So, the block transfer, so when you do a block transfer it can result in three things. One is successful completion, that is both all copies are copied, and partial failure is destination block has incorrect, that is this is during transfer. So, when the transfer is working there is no failure, then successful completion. Partial failure is the destination block, that is where you are going to send it to, that has incorrect information, and total failure is destination block was never updated. So, these are the three issues that can happen, and protecting storage media from failure during the data transfer, that is what we want to do. So, when the data transfer is occurring, we want to protect the storage from failure. For this you can have two approaches. One approach is execute the output operation as follows. What do? You assume that you have 2 copies of the block and you write the information onto the first physical block. Okay. Then you, when the first write successfully completes, write the same information into the second physical block. So, you finish one and then write the second. Now, the output is completed and you say that the transfer is completed only after both the write operations are completed, because one is completed you do not say. So, the atomicity of the operation is that both the copies are created, only then you say that the operation is complete. So, copies of a block may differ due to failure during the output operation. So, when you are writing, what will happen? You have written the first block, during the second block failure occurs. If that happens, the copies of the blocks will be different. So, there what you do is you recover from failure. So, for recovering from failure, now, so we assume that we want multiple copies, during the output operation some problem occurs. So, you have a failure. To recover from this failure, you have to find the inconsistent blocks. That is, if you have multiple copies of the same block, stored in 2 different places, then what you want to do? You want to find whether there is inconsistent blocks. There are 2 solutions to this. One is an expensive solution and the other is the more realistic solution. So, the expensive solution is compare the 2 copies block by block. Every disk block you compare, this block you have copied in 2 places, whether the 2 copies are same, but that is a very expensive operation. So, you go for a better solution. What is the better solution? When you are the record in progress disk writes, when disk writes are happening on non-volatile storage like non-volatile RAM or special area of disk, use this information during recovery to find blocks that may be inconsistent and only use that, only compare those copies. Do not compare each and every block, but compare only those by looking at the record in progress of the read writes, and when you have failure you know which block was during that time and that alone you compare. This is used in, later on we will be seeing in hardware RAID systems. Now, if either copy of it, now what happens? You have found the inconsistent block. After that what you have to do? If one of the copies of an inconsistent block is detected to have an error, override by the other. So, you have copy 1, copy 2 and one of them is inconsistent, then you overwrite the error block by the other one. If both have no error, but they are different, okay, then what you do? The second block you assume is more recent and you overwrite it by the first block. And then a database, now before we go further, I have said before we started that we are going to talk about blocks. Okay. So, database file is partitioned into fixed length storage units called blocks. So, all operations of data transfer occur in forms of blocks, which we have already discussed before. So, blocks are units of both storage allocation and data transfer. So, when a database asks for a storage, it is the block that is allocated, and when data transfer is occurring from main memory to disk and all that non-volatile memory, that time also we are doing it in terms of block. So, database system, one of the aims of a database system is to minimize the number of block transfers between the disk and the memory. So, how can we reduce this? We can reduce the number of disk accesses by keeping as many blocks as possible in the main memory. So, if we, in an idealistic situation, we would like to keep all blocks in the main memory, but that is not possible. So, what we want to do? We choose to keep the blocks in main memory such that you have minimum number of disk accesses. So, we talk about 2 things: buffer. Now, what is a buffer? A buffer is a portion of the main memory which is available to store copies of disk blocks. So, you have a buffer, in the buffer you will copy the disk block, and you have a buffer manager which is a subsystem which is responsible for allocating buffer space and also in the main memory and also for releasing, we will see that later. So, this buffer manager will be called whenever there is a need for a block. Okay. So, you need when you need a block. So, that time you will call. So, let us look at buffer management in detail. So, when you look at buffer management, buffer manager does the following. What it does, if the block is already in the buffer, remember the buffer is available in the main memory. So, I am calling for a disk block. When I call for a disk block, first thing I have to do is I have to check whether the disk block is already in the buffer. If it is already in the buffer, then you return the address of the block in the main memory. If it is already in the buffer, you address that, it is already in the main memory. So, return that. If the block is not in the buffer, that means it is not in the main memory. That time what we will have to do? We will have to allocate space in the buffer for that block, because the block is needed. So, how do we get this space? because there is a limited space only. For doing that, what we do, we replace or we throw out some other block, it is a block that is already present in the main memory, we shift it out into the secondary memory, and so that you can make space for the new block. So, that is how it is done. Now, the question asks what happens to the replace block. So, the replace block, that is the block that you are throwing out, in other words, or you are removing from the main memory, has to be written back to disk, but you will write it back to disk only if it has been modified. If it has not been modified, that is the recent time it has been done. If it is already available in the disk and no modification has been done, then you do not have to write it. Now, when we read the block from disk to buffer and then what do you do? So, first what we did, we found when you ask for a block to be placed in the buffer, you look whether there is buffer space available. If it is available, allocate it. If it is not available, then you have to take a block that is already available in the main memory, push it out, and then when you are pushing it out, you have to rewrite it, replace it on the disk if it is not changed. If it is changed, if it is not changed, you do not have to do anything. Then you allocate this block to the buffer and return the address of the block in the main memory. Now, the question comes, so how do we decide that we have to which block to replace? Now, what will happen is, if you do not replace properly, what will happen? You would have pushed one out, you need that again, and so on and so forth. So, the number of disk accesses increases. So, buffer managers, another job is to use some information to see that you do not push out blocks that will be immediately needed. For that, what the buffer management does is, buffer management will use statistical information regarding the probability that the request will reference to a particular relation or in where that block is stored or that relation is stored in a block. For example, a data dictionary, this is frequently accessed. So, always keep the data dictionary blocks in the main memory, never use it for replacement. Sometimes what buffer managers do, buffer management will also support forced output of the blocks. So, for recovery purposes, we always write certain things, forcefully write it. When we are finishing an operation, we forcefully write it into the disk. So, that job is also buffer manager's job. Now, comes the buffer replacement. We said that when a buffer needs to be allocated in the main memory, we need other blocks to be replaced. Now, how do we choose the replacing? So, most operating system replace the block which is least recently used. It is called the LRU strategy. So, I have a time and the time at which each block is used. So, from that information I can get the one that has been least recently used, that is the one that has been used much before. Then the idea is that you use the past pattern of block references as a predictor of future references. So, if it has not been used in the past, then there is no less chance of it being used in the future. So, that is the concept you are going to use. And also that you have queries have well defined access patterns. For example, some of them will be sequential scans. So, this information can also be used to predict future references. Now, LRU that is the least recently used need not always be a good strategy. It can be a bad strategy for certain access patterns involving repeated scans of data. So, when you are computing the join of two relations R and S by nested loops, for each tuple TR of R do, for each tuple TS of S do, if the tuples TR and TS match. Now, what happens if you had pushed out whatever that big block of TR, then the problem is this is not a good least recently used is not a good problem. So, normally for replacement they use mixed strategy, and you have something called pin block, that is memory block that is not allowed to be written back to disk, that is it is always has to be in main memory, and you have tossed immediate strategy, certain blocks that after you just final tuple of that block has been processed, then you can immediately push it out into the disk. And you also have what is called a most recently used strategy, where it will pin the block that is currently being processed. After the final tuple of the block has been processed, the block is unpinned and it becomes the most recently used block. So, this most recently used block is also another information that we use for replacement. So, up to this point we have spoken about basically blocks and how this axes are important and buffer management. Now, let us go into another important aspect which is called as file organization. So, file organization is a very important concept as far as database is concerned, because most of the data of databases is stored in files. Okay. So, let us look at the file management. So, the database is stored as a collection of files, and each file is actually a sequence of records and a record is a sequence of fields. So, basically you have files, within files you have a sequence of records, within records you have a sequence of fields. So, one simple approach is assuming that the record size is fixed and each file has records of only one particular type. So, all records are the same type, homogeneous as you call it, and different files are used for different relations. Relation, you remember from the database viewpoint, is a table. Okay. So, different files are used for different tables. This particular assumption makes it very easy to implement. We will see about other types of file organization later. So, let us first look at fixed length records. Now, this uses a very simple approach. So, it stores a record I starting from byte n into I minus 1, where n is the size of each record. The first will start at 0th, the second at 1 and second at 2 and so on. So, the nth record will be or the fifth record will be stored in n into 5 minus 1, 4, simple this thing. Record access is also simple, but the problem is records may cross blocks. See, because remember everything, the data transfer, the data allotment, everything is in terms of blocks. Okay. So, what will happen is this case, because it is fixed length, it may cross the boundary of blocks, and this we do not want it to happen. So, we want to do a modification such that we do not allow records to cross block boundaries. So, for that what do we do? So, first before we go to that, let us look at a case of a deletion of a block. Now, look at this, this is record 0 and then you have 3 attributes A whatever, this A1 and these are 3 attributes. So, suppose you want to delete record I. Okay. So, what you do is, suppose you want to delete record 4 for example, then you move record 5 up. So, move record I plus 1 to n. So, 5 to 8 up to I and n minus 1. And then that is one approach. Another approach, you move the 8th record to the place where you are deleting, and you can link all the free records, that is 4, this is a empty space. So, that you can replace it, and as you do deletion you can maintain it as a linked list. So, this is a simple case of fixed. Then you have the free list, you store the address of the first deleted record in a file header and use this first record to store the address of the second deleted record and so on. So, can think of these stored as pointers, since they point to the location of a record. This is similar to the free list that you had when you studied data structures. So, but this is not a very space efficient representation. What you can do is you can make it more space efficient by reusing space for normal attributes of free records to store pointers. So, you do not have to put pointers in use records. So, this no extra space is allocated. So, that is another way of doing it. So, this is the free list is actually a representation of all the free locations. If you look at here, you have a header points to record 1 storage is the storage of a deleted record, and if you look here, you have an additional pointer field. So, the record 1's that pointer field, free list pointer field, points to record 4, and record 4 again points to record 6, and record 6 is over. So, these 3 now, I mean this is the header, these 3 records have been linked as a free list. So, that is how free lists are maintained, and you can later on take, when you want to insert, you can take it from this free list. So, that is about fixed length. Now, let us look at variable length records. Now, variable records arise in database system. Why do we need a variable length? In several ways. So, you have multiple record types in a file. Okay. So, and there are record types itself that will allow variable length fields, each field can be different, okay, and record types that allow repeating fields. So, this was used in older data models where you can have repeatings. So, in all these cases the size of the record is not fixed. So, you use what is called a slotted page header for representing variable length records. So, the sorted page header contains the number of record entries, and it also indicates the end of the free space in the block and the location and size of each block. So, this information is stored in the header. So, so records can be moved around within a page to keep them contiguous with no empty space between them, but in that case the entry in the header must be updated, and pointer should not directly point to the record, instead they should point to the entry of the record in the header. So, you do not directly point. So, let us look at how this is done. So, this is the header, if you look here, this is the header. you have the number of entries is given here, and then for each you have the site and the location, and so on, and this indicates the end, this is the free space, and this indicates the end of free space. This is where the records are actually stored. If you look here, you have variable length, I mean variable sizes, and this says this record is stored here, this record, this points to this record, this points to this record, and so on. So, this is a case of where you have variable length records. So, this is called as slotted page structure, and another way of organizing records in files is using a heap. So, here a record can be placed anywhere in the file where there is space, otherwise it is called as sequential, where you store records only in sequential value based on the value of the key of each record. So, this is another way of doing. So, when you do organization of records in files, I said that you can use hashing. So, a hash function is computed on some attribute of each record, and why are you using the hashing? The hash function will tell you where you have to search for the block. So, each of the relations I mean the table may be stored in a separate file. So, or you can have a multi-label clustering file organization, where records of several different relations can be stored in the same file. So, store related records on the same block to minimize I/O. So, if you have different files, what will happen? These files may be stored in different blocks, and for if you have a database operation that operates on 4 or 5 different files, then for each of the files you need to have different disk operations. So, that becomes a costly affair. So, in order to keep all the type of files that you need, records that you need for a single database application in the same place, you can do this, store related records on the same block. Now, let us look at sequential file organization. This is suitable for application that requires sequential processing of the entire file. As the name suggests, you can just see it is just sequentially stored one after the other. So, and you can access this, it is ordered by the search key, whatever the search key here is here. Here the search key is based on the alphabetical order of the town names. So, deletion here, you use pointer chains for deletion. Insertion, locate the position where the record is to be inserted by following the free chain. If there is free space, you can insert it. If there is no free space, then you have to insert the record in an overflow block, which is a separate block that is given as part of the free list. In either case, the pointer chain has to be updated, and what the problem is, you have to reorganize the file from time to time in order to maintain the sequential order. Otherwise, all the time you will be going, you will be following chains, and that will be a long process, but the reorganization itself will take a lot of time. So, this is the sequential file organization continued. So, here you have a deletion file that has been deleted, and that is put here. So, this is the sequential file organization, and if you have multi-table clustering file organization, you have to store several relations in one file using that multi-table clustering, and for example, you have the example of a multi-table clustering file organization. This is good for queries involving depositor and customer, and one single customer and his accounts, and so on. So, but if you have a query where only we are talking about customers, then this is not a very good file organization. So, it depends on the type of queries that you normally have. Another important aspect of database management system is the data dictionary storage. This is also called as the system catalog, and it stores all the metadata. That is, it stores data about the data. What are the types of data that you have, metadata that you have? What are the names of the relations of the tables? The names and types of attributes of each relation, the name and definitions of views, we have already seen what are the views, and all the integrities contains. All this is about all the tables in the all the relations in the database. So, this is called as metadata. This type of metadata is normally stored in the data dictionary. User and accounting information including passwords is also stored there. Statistical and descriptive data, that is how many tuples do you have in each relation, how many records do you have in each relation, that is also stored there. And the physical file organization, how the relation is stored, is it sequential, is it using hash table, is it using whatever, and what is the physical location of the relation, that is also stored, and also information about the indices. All this information comes in the data storage. For example, a possible catalog structure is a relational representation on disk, and specialized data structures designed for efficient access in memory, both are this. So, relation metadata, what is the relation name? If you can see here, relation name, number of attributes, storage, organization, location, relation name, attribute name, domain type, position length, user name, encrypted password, group, index, relation name, index type, index attributes, view metadata, view name definition. All these are metadata about the data. So, after that we will look at what we mean by data access. So, what we see how the files are organized and the importance of data dictionary. Now, let us go into data access. So, data access are physical blocks are those blocks residing on the disk, buffer blocks are those blocks that are residing temporarily in the main memory. Because why are we saying temporarily? Because after the operation is done, it has to be necessarily written onto the disk. Block movements between the disk and the main memory are initiated through the following two operations. One is input B, transfer the physical block B to the main memory, that is to the buffer. Output B transfers the buffer block B to the disk and replaces the appropriate physical block there. So, this is what if it is already existing, it will replace it. Each transaction Ti has its private work area in which local copies of all data items are accessed and updated by it are kept. So, Ti's local copy, that is a transaction's local copy of a data item x is called as x of I. We assume for simplicity that each data item fits in and is stored inside a single block. This is just for understanding, obviously you can't do that for each data item. Now, transaction transfers data items between the system buffer and its private workspace using the following operations. Now, please note that this is only for between transaction manager and the buffer manager. So, read x assigns the value of data item x to the local variable, write x assigns the same thing to the data item in the buffer block. So, copying into the buffer block. So, this may initiate an input bx, that is writing of getting a block and so on. So, these operations are between. So, now we are having three levels, one is data, then block and then the transfer to the main memory or disk. Perform read x while accessing x for the first time and all subsequent access are to be the local copy. So, why are we doing this local copy? So, that after the last access the transaction will execute x, this we have seen before. So, what we are trying to do here is after this write operation we are writing it into the buffer and if the buffer becomes full or becomes thing, it will be put and it will be put into the main memory, physical memory. So, we are just connecting the three operations. So, if you look at this, you have a transaction and you have a work area, you have transaction, you have a work area and here you have the read x and the write y and this is the buffer block and this is to the this is which is available in the main memory and this is the disk. So, all these are to be a data access. Up to now we have looked at three things. We have looked at data access, we have started with summarization of the recovery algorithm, then we looked at storage structures, then we looked at file organization and then we looked at data access, actually what happens when a transaction is occurring. So, after that we will look at other issues in the next lecture. So, in this lecture we have first explained the various storage structures and we have explained it from the file organization viewpoint. We have also spoken about the different buffer replacement policies, that is how you choose a buffer to replace when you want to bring in something else from the physical storage. And we have also talked about the different types of file organizations and how files are stored, because all these factors are going to affect your database management efficiency. And we have also looked at different types of data access, how you do data access, for example, from the transaction onto the block onto the physical storage. So, some exercises have been given to you, expected to describe the various type of storage structures and explain the issues in implementing each of those storage structures. So, you will have to look a little beyond what has actually been covered in this lecture. Explain what is the least recently used buffer replacement policy and probably write a small algorithm for that. And I have asked you to list the various types of file organizations. So, thank you.